Lesson 6.5, linear functions. Our objective for this lesson is to be able to write an equation for a linear function that models a real-world situation. So let's define some terms. First, linear function. A linear function is a function with a constant rate of change. Remember, we defined a function in lesson 6.3 as a relationship between two quantities, where one quantity depends on the other. A linear function is one where the rate of change is constant. So now we need to define rate of change. Rate of change is the change in the dependent variable relative to the change in the independent variable. So we can write that as this formula. Rate of change equals the change in the dependent variable divided by the change in the independent variable. Remember that we often use y for the dependent variable and x for the independent variable. So this formula becomes the change in y divided by the change in x, which you may recognize as the formula for slope. The graph of a linear function is a straight line, and the rate of change is the slope of that line. All right, finally, initial value. Initial value is the output value of a function when the input value is 0. So remember, the output is the dependent variable, the input is the independent variable. And again, we often use y for the dependent variable and x for the independent variable. So initial value can be thought of as the y value when the x value is 0. And if you picture that on the graph, when x is 0, that's where the function is crossing the y-axis. And so we often refer to this as the y-intercept. The general formula for a linear function is given here. The dependent variable, for which we often use y, is equal to the initial value plus the rate of change times the independent variable, for which we often use x. So that's our general formula for a linear function. Let's now use that formula as we do our example. The example says, alcohol is metabolized by the body using enzymes in the liver in such a way that the blood alcohol content decreases linearly. A study by the National Institute on Alcohol Abuse and Alcoholism showed that for a group of fasting males who consumed 4 drinks rapidly, the blood alcohol content rose to a maximum of 0.08 grams per 100 milliliters about an hour after the drinks were consumed. 3 hours later, the blood alcohol content had decreased to 0.04 grams per 100 milliliters. Find a linear model that describes the elimination of alcohol from the blood after the peak blood alcohol content is reached. And then we're going to use that model to determine the blood alcohol content 5 hours after the peak is reached. All right, so first of all, let's decide to use y as our dependent variable, and we'll use x as our independent variable. And now we need to decide which one is which. We have 2 variables in this scenario. We have blood alcohol content, and we have the amount of time that has elapsed since the peak blood alcohol content was reached. And we need to decide which one is the dependent variable and which one is the independent variable. Well, here the blood alcohol content depends on how much time has elapsed. And so that's going to be our dependent variable, our blood alcohol content. And then x is the independent variable is going to be the time in hours from the point, the peak blood alcohol content. And so our initial value is going to be the dependent variable, the blood alcohol content, at time 0. And we're measuring time from the point that the peak blood alcohol content was reached. So our initial value is going to be that maximum of 0.08. And so then next, after we found our dependent variable, our independent variable, we've got our initial value. Now we need rate of change. Our rate of change is going to be the change in the dependent variable. So what happened with our blood alcohol content? Well, we started at 0.08, we ended at 0.04. So we're going to take our ending amount, 0.04, and subtract our beginning amount, 0.08. That's going to give us the change in blood alcohol content over that time. And we're going to divide that by the amount of time that has elapsed. So we started, at the time when the blood alcohol content was 0.04 was 3 hours. 3 hours later, and the time for the 0.08, that was at our 0 point. So over 3 hours, our blood alcohol content has changed from 0.08 to 0.04. So if we subtract these, 0.04 minus 0.08 is negative 0.04, and we're going to divide that by 3. And that's going to equal negative 0.0133. All right, so that's our rate of change. We now have rate of change, initial value, and we've determined what our dependent and independent variables are. Now we can just plug it into this general formula. We have our dependent variable, which is y, is equal to our initial value, which is 0.08, plus our rate of change, which is negative, so we're going to say minus 0.0133, times our independent variable, which is x. So this will be our model that we will use. And now we're asked to find out what would be the blood alcohol content after 5 hours. So all we have to do now is just plug in 5 for x, for our independent variable. So we're going to get y equals 0.08 minus 0.0133 times 5. And if we plug that into our calculator, we're going to get that y is equal to 0.0135. So that's going to be our blood alcohol content after 5 hours according to our model.